We will start our discussions with defining measurements, understanding what are measurements and what are not, which will lead us into exact and inexact numbers. It will also lead us to our very important discussion of significant figures, a review of scientific notation, and also discussion of how do we use scientific notations and or significant figures in mathematical calculations involving measurements. Okay, so let's start with first identifying measurements. What makes a number, something, a measurement? Here are some examples of measurements. I'm sure you can think of several more on your own. Um, I'm sure some of you might think of 70.5 miles per hour, or how about 3.060 grams per cc, or 90 amps. There are so many measurements out there that we use on an everyday basis. So before we define the term measurements, I would like for us to consider what are the different parts to a measurement. What is a measurement made up of? A measurement will have a number, a value associated with it. This is called the magnitude, the size of the number, the value of that quantity that you are measuring. All measurements will have a magnitude. All measurements also have a label that describes the property that's being measured, a label that is a standard across every scenario. In this case, liters, we know liters is measuring volume, miles is measuring distance, minutes is measuring time, pounds is measuring weight, so on and so forth. So this label, which also every measurement must have, is called a unit. There's a third part to every measurement which most of the times we don't write, but we know always that it's there, because every measurement will also have something called an error. Now let me explain what this means. Now if you have 25 liters of a liquid, could it actually be 24.8 liters instead? Could it be actually 25.056 liters? Absolutely. That's the error. That is, every measurement has a range within which the actual value of that quantity lies. Okay, so all measurements have magnitude, error, and units. Now, before we go on, let me give you a couple more examples to help you identify, to help you distinguish between a measurement and something that may not be a one. So, how about 25 pencils? Is this a measurement? Now, let's evaluate. Does it have a magnitude? Yes, it seems to have a magnitude. I mean, it has a number, a value. Yes. Does it have a unit, a label? As long as all the pencils are exactly the same, yes, that can be a label, a unit. What is it that this example does not have? An error. This example does not have an error, which means basically instead of being 25 pencils, could there be 24.9 pencils? Or maybe it was 25.2 pencils. No, that's not possible in this case. So because that is not the case, 25 pencils is not a measurement. So what is a measurement? Let's define the term measurement. Measurement is any quantity that is determined with the use of an instrument. No matter what kind of an instrument it is, but if an instrument is being used, a tool is being used to determine something, then that would be called a measurement. If not, how did we determine 25 pencils? By simply counting them. Then that number is not a measurement. Instead, that number is called a counted number. Here are some more examples of counted numbers, which are once again determined simply by counting 12 eggs, 13 potatoes, 25 children, so on and so forth. Okay. Now there are some numbers that are exact numbers while others are inexact. A number that has no ambiguity, no uncertainty associated with it is called an exact number. And all counted numbers are exact numbers, whereas a number that has a certain degree of ambiguity or uncertainty associated with its value is an inexact number. All measurements are always inexact. So please do remember that counted numbers are always exact numbers, whereas measurements are always inexact. This also then brings us to a couple of other terms that need to be defined and understood: accuracy and precision. Accuracy is a term that identifies how close a measurement or an average of a set of measurements is to the actual value of that property. Precision, on the other hand, is a term that represents how close a certain set of data are to each other. For example, let's consider a dartboard. A dartboard has several layers of point values, and the closer you get to the center, the higher is the point value. Let's say a player throws several darts, but they are all close to each other, but not close to the bullseye. Those set of data will be precise. There's a high degree of precision, there's a high degree of reproducibility, but not accurate. Let's say another player throws darts, several of them, that are all over the board. These set of data are neither precise and nor accurate. But there is one player who is so good at this game that when he or she throws their dart, they all end up very close to the bullseye. That player has collected a set of data that are both precise and also accurate. So the difference between the two terms is the comparison point. In precision, you're comparing the data points to each other within the order of precision allowed by the instrument, whereas in accuracy, you're comparing the data collected to the true value, the actual value. Now, as we said before, that measurements are inexact numbers because all measurements will always have a certain degree of uncertainty or ambiguity associated with them, because no instrument can give you an 100% accurate answer. There's always a certain wiggle room. Let's take an example of a bag of apples bought at a grocery store. And if we weigh that bag of apples at the grocery store using one of their scales, let's say the balance reads 5 pounds. But if I take the same bag of apples to a weighing scale in a chemistry laboratory, it reads 4.855 pounds. What's going on here? Did we lose some apple from the grocery store to the laboratory? Or maybe the grocery store lied to us and told us we had more than what we actually did? None of those cases actually is what's happening here. The balances at both places are working just as they're designed to. The bag of apples didn't actually lose any apples. It's that every instrument has its own order degree of precision that it's designed to read a measurement in, and that is the limitation that every measurement would have. So every measurement is limited in the precision that it can record a certain measurement in by the instrument that is being used. And we have to be very cognizant of that and very careful of that. So every measurement will have an error associated with it. In other words, let's look at the examples that we saw before. Which weight is more accurate, 5 pounds or 4.855 pounds? For obvious reasons, I'm sure you will all recognize that 4.855 pounds is a way more accurate answer weight for that bag of apples compared to 5 pounds. But why is it? Why is the 4.855 pounds more accurate than 5 pounds? Because given that all measurements will have an error associated with them, let's take another set of weights for a bag of apples again. The only thing that's changing from one of these to the next measurements is the balance use. It's the same bag of apples. It is the same user. The balances are all working as they're calibrated to be. It's just that the balances are different. So then which measurement will be most accurate? 4.87817 pounds. But why? The reason for that is that the error in a given measurement always lies in the last reported digit. Now, this is a statement that I will very shortly make more specific, make it more accurate, I guess, in a way. So please keep that in mind. For now, we'll work with the statement that every measurement has an error, and that error lies in the last reported digit. So taking the first example of 5 pounds, now I'm going to erase the unit for just a few minutes because I want us to focus on the magnitude. Which place value is the last reported digit in the ones place? So the error will be in that place as well, plus minus 1 followed by the unit. Basically what it means is if the balance says 5 pounds, the actual weight of that bag of apples can be anywhere from 4 to 6 pounds, in that range. That's the precision allowed by this balance. In the next one where it says 4.8, the last reported digit is in the tenths place, the first decimal place. So the error will also be in the first decimal place. In other words, the actual mass of the weight of this bag of apples can be anywhere from 4.7 to 4.9 pounds. The error in the next one will be plus minus 0.01, and the last one will have an error of 4.8 in the third decimal place, so 0.001 pounds. So as you report more digits, the error becomes less. The precision of that measurement goes higher. Okay. So let's take these examples. The question is very simple. That is to give the error associated with each of these measurements. Please remember that the error, at least for now, we will change the statement very shortly, but the error for now lies in the last reported digit. So this one will have an error of plus minus 0.01, plus minus 0.001, plus minus 0.0001. Now the last example is actually a very tricky example, and I would like to save this example for later, for when we have done something called significant figures. That is when we will modify this statement and make it more meaningful.